Okay, thank you, Maran. Jeremy, you have a question?
Yes, thank you for the great talk.
Thank you.
I was wondering if you could have or does this let us work towards a concept of entropic complexity for problems as well as circuits, or is it mostly a definition for circuits?
So we are working towards that. It's a long ahead, but yeah, I mean, we will do that, something similar. I mean, the next step would be relating like circuit complexity classes, for example, NC with mismatch cost complexity, but yeah, working towards that.
Just a quick follow-up to that. Like a lot of the older papers seem to say like you can compute things reversibly, and in that limit you wouldn't have maybe I'm wrong, but you wouldn't have like a cost.
No,
But
yeah.
is that relevant in this case, or is there?
I don't think it's relevant, but I'm not sure how you can compute things.
Okay, maybe I can,
Mm.
I'm waiting there. Takahiro was mentioned before, Takahiro Sagawa. He's got a great paper, very, very easy to read, called Logical and Thermodynamics of Reversibility Revisited. Fantastic paper. You can read it in like 20 minutes. Basically, a lot of the great intuition of Landau and Banach concerning things like reversible computation, at a minimum, things are much more complicated, and arguably all that's wrong. Running things reversibly doesn't allow you to get around problems if you're going to actually use your system more than once. Concerning the earlier question about just the computational complexity of problems per se, normally that means running things on a Turing machine. The way, P, NP, and stuff like that. Artemy, in fact, has done some really nice papers on thermodynamics of the partial functions implemented by Turing machines. I've also done some of that, but nobody has yet actually done anything on the thermodynamics of a Turing machine in the sense of here is a tape that is being changed, here is a head that is changing its states and moving around the tape, and then you need to run it forward and backward. Or more precisely, people like Strasbourg and Tom Aldridge and so on have looked at specific models of that, like Brownian systems and so on and so forth. But nobody has done general results. Artemy's results are for the partial function it implements, and they're very broadly applicable. And those other people are for the full Turing machine, but they're very, very special case. So all that's work to be done.
Thank you for the answer.
Do we have time for a few more questions if there are any? And if not, then perhaps to save a bit of time, we can get back onto schedule closer. We can just start the next talk. Aram, are you ready to go?
I think so. Let
Okay.
me. You guys can see the slide, right?
Yep. And you can have an extra 2 minutes, I guess, if you need to. Otherwise, we can actually get a little closer to being on time. Go for it.
Okay. So, um, basically where we start off is stochastic thermodynamics, and it's like just it's amazing success at for studying all sorts of non-equilibrium systems at all sorts of scales, bringing these three fields here together. The only problem I have with how we're doing things is that we define entropy in terms of probability distributions, which is useful, but it does raise questions like, does that mean entropy is subjective? I mean, you guys know, like, if you're told the state of the system, does that mean its entropy suddenly decreases to zero? Can a deterministic computed memory, does it even make sense for a deterministic value to have entropy? So the goal here is just to see if we can define entropy for individual states. We don't want to depend on distributions. We also don't want to depend on macro variables like in the usual Boltzmann entropy picture. And in doing so, we hope to deepen the marriage of thermodynamics with information theory. Just a small caveat, though, this is going to be a classical discussion, not a quantum one. So before introducing this algorithmic thermodynamics, which will be kind of our proposed solution, I want to kind of review stochastic thermodynamics in the most minimal, simple way, just to give us the assumptions we need. So we have a phase space. We partition it into coarse-grained states. Let's call them X, Y, and so on. There's a Liouville measure pi. We evolve a Hamiltonian for some fixed duration. And what that does is it induces a mapping on this phase space. So I've drawn here like 3, let's say, coarse-grained states. The mapping should be invertible. It should preserve the Liouville measure. And so now let's define the matrix P of Yx. The notation is suggestive, but right now this matrix just denotes the fraction of the region X that maps into Y. So if you sampled uniformly from X, then you could interpret this as the probability that you'll map to Y starting from X. But you really would have to start uniformly in X. So we have to be careful there. Conversely, P tilde denote that that denotes the fraction of Y that is mapped from X. So here we have the picture. So the inner region, the specific part of X that maps to Y has volume P of Yx times the measure of the whole X, and similarly for Y. And these two regions map 1-to-1 to each other. So by Liouville's theorem, their measure has to be equal to each other. So we have this identity. This is just Liouville's theorem. And if you sum this identity over all X, you get that the measure pi is stationary. So this looks a lot like Markov chain theory, except that we haven't really justified interpreting these P's as probabilities. So let's actually add that as an assumption, a postulate. So we're going to assume that this matrix really does represent conditional transition probabilities when we go forwards in time. This is actually very analogous to the molecular chaos assumption. It is an assumption that breaks time reversal symmetry because we do not assume the reverse version of this. P tilde is not the backwards transition probabilities. This is kind of it's kind of a mysterious assumption. But it does seem to be very important in stochastic thermodynamics, at least in a lot of the treatments of it. And in some simplified models, we have other work showing that if you assume a certain kind of statistical initial condition, then you can prove MCG, but only in these simplified models. And in those models, you also get a causal arrow of time. So there seems to be something very deeply intertwined with the arrow of time and this MCG. Another assumption we don't make is detailed balance. That makes our treatment a little bit more general. So it just means that this has nothing to do with the arrow of time. This is a different asymmetry that has to do with the fact that you could transition from X to Y, and that doesn't necessarily imply you could transition back from Y to X. So this happens if you have something like momentum, say, where you could go from X and then from X you go to Y, but then from Y you go to Z. You don't go back to X because the momentum keeps you going in one direction. So this is just for more generality. So in summary, with this MCG assumption, our dynamical system is now just a discrete state Markov process with a stationary measure pi, and we can use stochastic process theory. We define the stochastic entropy relative to this Liouville measure pi by this log ratio of the Liouville measure and the probability mass on X. Now this might look a little different from how some sources define stochastic entropy. The reason is, one, we're not specifying the units, which are kind of hidden in the choice of the logarithm space. So you could us information theorists like to use binary log, but you could use natural log and put a Boltzmann's constant in front. That'll give you the value in physical units. The other difference is that usually this formula can be broken down this way. And usually maybe we only call the first term, the log 1 over mu, the stochastic entropy. And the second term we associate as being the kind of the Boltzmann entropy of the surrounding heat bath. You could do this, and that's fine, but then the second law only applies to the sum of the two anyway, so we really only care about this log ratio. So that's going to be our definition of stochastic entropy. If you average that over the whole distribution, that's called the Gibbs-Shannon entropy, again, suitably generalized to be relative to pi. So now if you use the MCG postulate, you can prove fluctuation theorems. You can get a second law. The Gibbs-Shannon entropy does not decrease. And in fact, with overwhelming probability, the stochastic entropy cannot decrease substantially either. So none of this is new to you guys. This holds fall out of equilibrium. This is an amazing set of results. However, as is made very explicit in this notation, both of these entropies depend very explicitly on the probability distribution mu. And I don't know of any universal recipe for getting mu. If there is, I'd like to know. But so I want entropy to just be a state function, just like energy is a state function, just like most physical things are. So here's one way to do it. We're gonna define informally, we're gonna think of the entropy as being the amount of information needed to specify a coarse-grained state. So given a state, just come up with some standard text representation. So if X represents the state of some box of gas, then imagine listing out every particle's position and momentum up to the coarse-grained accuracy. That's a valid text representation that you could give to a computer. This representation might be redundant, it might be compressible. So Kolmogorov defines the description complexity as the length of the shortest computer program that produces this representation. So of course, this will in general depend on the representation and the programming language. We argue that as long as you make intuitively reasonable choices, this dependence is very, very small. And so for any macroscopic system, this is a well-defined thing. We could debate that later. But then you define, well, so there's a few notions of algorithmic entropy from the 80s and 90s. The best one, I think, is Petr Gatcha's algorithmic entropy. You take this, it's very compatible with this stochastic thermodynamics coarse graining, and you just define it as the sum of this description complexity and the log Liouville measure. You could think of this as kind of analogous to the stochastic entropy, except that we've replaced the log 1 over mu. Log 1 over mu can be interpreted as a code length, right? But we instead replace it by this universal code length, k of x. So now if we use the MCG postulate, you can prove a whole set of new fluctuation theorems and an algorithmic second law. With overwhelming probability, once again, but now with the algorithmic entropy, you find that it cannot decrease by a substantial amount. This applies to arbitrary states, no distributional assumptions. And this log delta t term is very small. You know, even if you weight the whole age of the universe, this is small. You really need, for this decrease to be substantial, you need to wait like ridiculous amounts of time, which is to be expected. Like eventually you do expect Poincare recurrence and all that. And the roots of this theorem are actually very, very old. Levin proved a kind of fluctuation theorem as far back as 1974, I think. The original paper is Russian. There's an English paper in 84 he wrote, and he called it randomness conservation. And this was not in a physics context, but the mathematics comes from that. So some of kind of bolder claims I want to make here. Is that the algorithmic entropy, I think, is the more fundamental entity we should be thinking on in terms of the philosophically correct thing when we talk about entropy. But the Boltzmann and Gibbs entropies are excellent approximations. And in nice situations, for nice distributions, and the X being typical for that distribution, we get that these two entropies are actually the same. And so it doesn't matter which one we use. But in the general case, we have this weaker relationship. And so what does this actually say? This says that, so if we treat S pi as kind of the correct entropy, then when we use Gibbs-Shannon, we're only getting the mean value of this entropy, and not just the mean, but also the mean conditional on prior knowledge of mu. So intuitively, the way I think about this is that, let's see what this means in practice, right? So usually when we have a real physical system, we imagine that we can manipulate it to extract work and so on. And when we do that manipulation, we kind of use knowledge of mu, we use certain macro variables. I mean, the question is what sort of manipulations are available to us? Like with this box of gas, maybe we can change its pressure and its volume, maybe we can compress it. And if we have a few things we can do like this, then it's kind of natural to like encode that information in our knowledge of the state. But I mean, I don't know, a gas is very chaotic and mixes very rapidly. Maybe there's not that much we can do with it. But if we have something more crystallized, like a computer memory, you can imagine there are systems where you can do all sorts of different manipulations. And the real question is, like, we don't want to have prior knowledge of mu. We want to just say, we have the state in front of us. We're allowed to inspect it. and perform kind of arbitrary but still coarse-grained manipulations. We have lots of time to do all the computation we need. The question is, what is the upper bound on the work we could ever possibly extract from this single individual state? And we show in the paper that this work is bounded by the Helmholtz algorithmic free energy, which is a similar formula to standard free energy, except that we've replaced the entropy term with this algorithmic version scaled to the appropriate units. Yeah, so just to give a preview, like there's a whole bunch of fluctuation theorems, relations you can show. The one over here is by Artemy Kolchinsky. Here there's an inequality that looks a lot like Jarzynski's equality, but but it uses only trajectory level quantities and this algorithmic free energy. Anyway, so that's it. That's the talk. I'd like this to be the start of some conversation, hopefully. So please do talk to me after this as well, whether about philosophical points or more practical elements. Yeah, thank you.